Alrighty. Welcome to our week 2 asynchronous lesson, y'all. Today, our learning targets are to, first of all, we're going to derive the unit circle. This is something that I left y'all off with last class period, and I wanted to show y'all the sort of final solution here. Once we've finished deriving the rest of these coordinates on our unit circle using the special triangles, we're going to discuss an idea called Radian Measurement. We're going to make sense of what that is, where it comes in, why is it relevant. And then finally, we're going to use this unit circle and our Radian Measurement, which will actually contribute to the unit circle, in evaluating some basic trigonometric functions, things that y'all might remember from geometry like sine, cosine, and tangent. So to get ourselves started, I'm going to, first of all, let's finish this unit circle here. So you notice that we have the first quadrant of the unit circle we have previously derived using these special triangles. If y'all don't recall, the way it worked was that essentially at any given angle on the unit circle, I could essentially drop a leg from that point on the perimeter, which creates a right triangle. Now, notice that this right triangle here has a 30-degree angle, and so therefore it is a 30, 60, 90 triangle like I have right here, right? And so what am I going to do with this 30, 60, 90 triangle? Well, we knew that the long side of that triangle would be the square root of 3 over 2 in length, and we knew that the shorter side would be 1/2 in length. Now, why is it root 3 over 2 and 1/2 when there's an h here in my formula? That's because it's called the unit circle for a reason, y'all. It's called the unit circle because the radius of this circle is 1 unit. Notice how the coordinates on the axes are at 1, 0 and 0, 1. So essentially h here is equal to 1. So that means that the hypotenuse of my 30, 60, 90 triangle within this guy here is 1, and those side lengths are root 3 over 2 and 1/2. We also use the 45, 45, 90 in order to get these coordinates here at the 45-degree angle. Essentially, if the hypotenuse was equal to 1, then what was k? You could solve this by dividing both sides by the square root of 2, right? Now, that would mean that k is equal to 1 over the square root of 2. However, in math, we tend to try to what we call rationalize our denominators. Remember, that was where we multiplied the top and bottom of this fraction by that square root of 2. And the reason why we do that is because then when I multiply these fractions, I get 1 times square root of 2 is equal to the square root of 2, and square root of 2 times square root of 2 is equal to the whole number 2. So in the end, k would be square root 2 over 2. And that's where we got these coordinates here for the 45-degree angle, right? So what we're going to do now is we're going to start off with understanding what all these angles are around the unit circle. All right. So the way I want to start off is notice a circle is 360 degrees, right? If I go all the way a circle, right? This line here at the x-axis, on the positives of the x-axis, is where we start, remember? And it goes around the circle. So this is both 0 degrees and 360 degrees because where I end up is at the same place where I started. These are called cyclic functions for a reason. They can repeat themselves. In fact, I could even go beyond 360. I could do another loop, and I'd reach the same spot at 720 degrees, technically. And that's a topic for another time, all right? So if the whole circle is 360 degrees, what would be half the circle? It is 180 degrees. And then what we can do is so that's half the circle. Now let's cut the circle into quarters. We can recognize that 1/4 of the circle was 90 degrees here, right? 2/4 was 180. So 3/4 would be 180 plus 90 is 270 degrees, right? So that was the quarters of the circle. Next thing we could do is we could talk about the eighths, right? Where's this 45 degrees? So when I go 1/8 and I'm here, I get 45. I go 1 more eighth, I get 90. Notice how 2/8 is 1/4, right? 2/8, right? Because this is 2/8 of the circle is equal to 1/4 of the circle. All right. Keep going. I get 3/8 here. 90 plus 45 would be 135 degrees. Keep going. Add another 45. I get 180. Add another 45 to that, and I get 225. Add 45 to that, I get 270. Add 45 to that, I get 315 degrees. What y'all will notice is I'm just adding my angles as I go around the circle. The last but not least one that we will do is we can go by 30s. Notice I've got 30, I've got 60, I've got 90. 90 plus 30 is 120. 120 plus 30 is 150. 150 plus 30 is 180. 180 plus 30 is 210. Plus 30 is 240. Plus 30 is 270. Plus 30 is 300. Plus 30 is 330. So I've got all the angles around these unit circles. Okay. So now all we got to do is find the coordinates around the unit circle. I could do this pretty easily because if I know the first quadrant, y'all, then I know everything there is to know. The nice thing about the unit circle is that you don't actually have to memorize the entire thing, guys. And in fact, I really don't want y'all to memorize it. Don't bother memorizing the whole unit circle. What's more important is that we understand how the unit circle was derived. This is why I'm teaching you guys how to derive it. Because if I can understand kind of where do these different measurements around the unit circle come from, then I don't have to memorize it. I can just always kind of remember how I got to this unit circle, and that will help me out in the future when I'm evaluating trigonometric functions and so on. Okay, guys? So let's try it out a little bit. First of all, it's really easy to do the ones that are on the axes, right? Because the unit circle has a radius of 1. I know that this coordinate here is -1, 0. And I know that this coordinate here is 0, -1. Okay, those are the easy guys. Now let's look at our some of our angles here. All right. First of all, I want to look at 135 here, and I want to use a new color. So I'm going to use this green. Remember, y'all, the 45 degrees right here was the 45, 45, 90 triangle like we had over here. And that triangle has side lengths of √2/2 and √2/2. This 135 degree angle, if you guys notice, it is the exact same triangle, simply reflected across the y-axis, right? Do you see that? It's been the same triangle reflected across the y-axis. It went from here, from this coordinate, across the y-axis over to right there. So what is this triangle side lengths going to be? It's the same ones, √2/2, √2/2. The only difference, y'all, is notice I'm in the negative x direction, right? This is the positive x's. This is the negative x's. So my x value should be negative square. Ooh, I didn't make these very big. Negative √2/2. And the y value, it's still in the positives, right? Because here's positive and here's negative. So the y value for this guy is positive √2/2. All right. Something that I'm going to do, guys, is I will post a link to a kind of cleaner version of this final unit circle in the description of this video. So if you are looking at my handwriting here and you're saying, damn, Mr. Hobaugh, it's kind of hard to read this, go ahead and go to the link that I'll have in the description of this video, and you can find a much cleaner version of the unit circle. But for now, I want to do it on my whiteboard just because I think it's important to kind of talk ourselves through it, okay? So continuing on, let's look at more of these 45-degree angles, right? If I look straight down below this angle, this coordinate, I can see here at 225 degrees, it is another 45, 45, 90 triangle, right? See, actually, guys, 225 degrees, one way to think about it is that it's actually 45 degrees beyond 180, right? 180 being where the y value is 0. So interestingly enough, what we can do is we can actually understand this coordinate as the same as my 45, 45, 90 triangle, except notice that its x coordinate is negative and its y coordinate is negative. So this guy is going to be negative square root 2 over 2, comma, negative square root 2 over 2. And what do you think the last one's going to be over here at, oops, not a very good line there. Over here at 315, something that we can notice, once again, bring the line up. It is a 45, 45, 90 triangle. 315 is actually 45 degrees less than 360. Right? Notice how it's 45 degrees less than 360. So the coordinates of this guy would be the square root of 2 over 2, because the x coordinate is positive, but then the y coordinate is negative root 2 over 2. So those are all of our 45-degree angles in their coordinates. Saying that, you guys will notice that it makes it actually, when you connect all the points, it makes this nice little box. It makes this square that connects them all. And I just think it makes a nice visual representation of connecting all of the coordinates. If you have different colored pencils at home, I would totally suggest drawing on a unit circle this connection with all the different, like, for example, I have all my 45-degree angles connected. I'm going to eventually have all my 30-degree angles connected and all my 60-degree angles connected, right? So speaking of that, let's try out the other angles. But before we do so, actually, I want to point out something, guys. Notice that the coordinates never truly changed. All that changed, or at least the absolute value of them doesn't change. Just the positives and negatives, the signs are changing. So something that's a really nice trick for remembering all these things, guys, is that any point in the first quadrant will have a positive x value and a positive y value. So I like to draw for myself just a coordinate pair with plus plus in the first quadrant. In the second quadrant, my x coordinate is negative, so I have negative comma plus. In the third quadrant, they're both negative. And in the fourth quadrant, the y is the negative. So I like to do this to kind of remind myself of what should my signs for my coordinates be, right? So next up, what I want to do, guys, is we're going to go ahead and let me change this from green. We'll use purple. Why not? Let's do the 30-degree angles. And I'll go a little bit quicker this time, since I think you guys kind of see the pattern that follows. Every 30-degree angle will have the coordinates root 3 over 2, comma 1/2. So this one is 30 degrees. 150, if you think about it, is actually 30-degree angle. It's 30 degrees above the 180, right? It's just 30 degrees less than 180. So it's actually going to have the same coordinates as my 30-degree angle, except with a negative x value. So it'd be negative square root 3 over 2, comma 1/2. Over here at 210, that is 30 degrees more than 180. It is negative negative, so it's going to be negative root 3 over 2, comma negative 1/2. And then finally, we have across here 330. That's a 30-degree angle less than 360, right? Drop that, and I see that, okay, it's a positive root 3 over 2, comma negative, oh, that's not positive. This is positive root 3 over 2, comma negative 1/2, right? So those are the coordinates for all the 30-degree angles around it in the purple box. Here, let me draw this in purple. The last one we need to do, guys, is the 60-degree angles. So why don't we do those in a different color? Let's use red. So from 60 degrees, right? See, here's 60 degrees. From 60 degrees, our coordinates are 1/2, comma root 3 over 2. If I go across and reflect this, right, I get a negative x value. So I get negative 1/2, comma square root 3 over 2. Saying that's an interesting little thing to notice here, by the way, guys. The 30-degree angle and the 60-degree angle are just flipped versions of each other. That's because the 30 and the 60 are both contained in the same angle. They're just on opposite sides. So from the perspective of 60 degrees, root 3 over 2 is the height and 1/2 is the height. But then from the perspective of the 30 degrees, let me do that in purple since we're using purple for 30 degrees. From the perspective of 30 degrees, 1/2 is actually the height of it, right? If you kind of turn your head, you can see that this is the height. And then root 3 over 2 is the length. Kind of just a little interesting fun fact there. All right, so keep continuing on with our 60-degree angles. If I go down from here, I can find that 240 is actually a 60 degrees more than 180, right? See that? So 240 here would be negative version of that coordinate pair. So negative 1/2, negative root 3 over 2. And finally, I go across my y-axis, and I'm at 300. And what we can notice is that 300 is actually, once again, guys, 60 degrees less. It's a 60-degree angle from 360. And so it has positive 1/2 for its x-coordinate and negative root 3 over 2 for its y-coordinate. And so here you have it, guys. This is our completed unit circle. Now, the thing about the unit circle, y'all, is that it has all these coordinates going around with the different angles. Now, these are not all the angles that exist in the world, right? In fact, they're not even all the angles that exist in the unit circle. Technically, I could have any angle here. I mean, that's kind of the point of it, is that it goes all the way around. It represents any right triangle, which we've talked about already. But it does have pretty much every significant angle we could want, right? I might not have, 23 degrees, but I've got all the, whole numbers that I might be actually concerned with, like 30, 45, 60, 90, and all the multiples of those. Now that we've kind of seen the unit circle, what we're going to do is we're going to talk about the next topic, which is radian measure. We commonly measure angles in degrees, right? And there just so happen to be 360 degrees in a revolution, right? So this kind of begs us a question here real quick. Why? Why are there 360 degrees in a revolution, right? Why is one full revolution 360 degrees? What has defined this? What is the purpose? The answer to that is actually twofold. There's two main reasons of why there's 360 degrees to a revolution. The first reason is that it's convenient. It just so happens that 360 degrees is a number with many factors. In fact, 360 degrees is divisible by the number 1. It's divisible by 2. It's divisible by 3. It's divisible by 4, 5, 6, not 7. It's not divisible by 7, unfortunately, but it is divisible by 8. It's divisible by 9, and so on. 10, 12, so on. The interesting thing here is that if you have a unit of measurement, right, like you want to measure circles and angles and such, it does come in handy when you're working with it, especially for things like engineering and drawing up plans. It comes in handy to have one full circle be some value, which is very easily divided into whole numbers, right? So that's why it's convenient for there to be 360 degrees in a circle. Now, the other reason why there's 360 degrees in a circle is just pure coincidence. Why did we decide to make circles have 360 degrees? Well, the first people in the world to really concern themselves in any meaningful application of measuring with angles and kind of greater values of, or greater applications of trigonometry were people doing navigation, people sailing around the world, people sailing in the ocean, where the only thing you have to guide yourself is the stars, right? So what happens is when you're looking up at the stars, here's the sun, right? And here's the earth. And what's happening is that we are rotating around the sun, and as we rotate around the sun at different points we are in different seasons, and in those different seasons, you see different stars, right? Or at least you see the stars from different angles. And so what sailors and so on needed to do was they needed to be able to essentially measure the distance which they had gone around the sun in terms of the angle, so that they could kind of apply that in their factoring of where am I in the world, right? Where am I, and so on. And how many days does it take to go around the sun? It takes actually approximately 360. So it's actually just a coincidence, because really this isn't the case for all planets. This is just the case for Earth. We just so happen to have a year, right? One full revolution around the sun takes us 365.25 days. And if you kind of round that to make it nice and easy, you end up with 360. So why do degrees even exist? Why are they 360 in a revolution? These two reasons: convenience and coincidence. So while we've been looking at revolutions and angles and angle measurement, it's going to be a pretty natural transition for us to start looking more at circles, right? So what I want to remind you guys is a circle has a circumference which is equal to 2 pi times its radius, right? So if I look at our unit circle, for example, our unit circle has a radius which is equal to 1 unit. And the circumference of this circle, right, the distance all the way around it, would be equal to 2 pi times its radius. Its radius is 1, so the circumference is 2 pi. It's 2 pi units around the unit circle, right? Now, what we're going to do is we are going to define one full revolution, right? One full revolution around a circle as 2 pi radian, which we oftentimes abbreviate as rad, because they are rad. Now, if one full revolution is 2 pi radians, then that means that 2 pi is equal to 360 degrees, right? Now, what I'd like to do is take a look at some more kind of portions of the circle and looking at, okay, how many radians is this segment, right? How many, sector. So if I have, for example, half of a circle, right? If I want to look at half of a circle, which is 180 degrees, that would be half of our 2 pi, our full revolution, which would be 1 pi. So 1/2 of the circle is defined as pi radians, right? What about a quarter of the circle? Now we care a lot about quarters of the circle because that is a right angle, right? And so what is a right angle? Well, it is 1/4 of the full circle, which is 2 pi. 1/4 of 2 pi would be pi over 2 radians. Now, we could continue on with this, but in order to look at kind of from our unit circle, for example, what are all those commonly useful angles to look at? We knew 90 degrees was very useful, right? Because that's the right angle, and we care a lot about right angles. We had 60 degrees, we had 45 degrees, and we had 30 degrees. These were all kind of our important angles that we were looking at from our special triangles. Well, we already figured out that 90 degrees was pi over 2 radian, right? It was pi over 2. Well, from that, we could kind of figure out what 45 is, right? Because 45 is half of 90. Half of pi over 2 would be pi over 4. Okay. What about 30 degrees? 30 degrees is 1/3 of 90, right? It's 1/3 of 90. So in order to get 30 degrees, I would need to do 1/3 of pi over 2, which would be pi over 6. And I could actually go from 30 degrees to 60 degrees by doubling it, right? Or I could recognize that 180 degrees is pi. And so 60 is 1/3 of that. So in the end, 60 degrees is pi over 3, y'all. Now that we've seen kind of some of these comparisons between radian and degree and how they kind of work together, what I want to do is I want to talk to you guys briefly about why do we care about radians? What are they? Where did they come from? Other than just me randomly defining a full revolution as 2 pi radians. And why might they be useful? Oftentimes when we introduce new math topics, it's kind of the common strategy to first kind of say, what is it? And then how do we use it? And then look at applications finally if we get there. But what I want to kind of do is reverse that. And so we're going to first off look at some of these applications of radian. And one common application when working in angles is looking at things like arc length here. So why do physicists care about arc length? Well, it's a sort of essential thing to be able to calculate when you're working with circular motion, when you're working in such patterns. And one particular example where we might see circular motion is in a centrifuge, which is what I have pictured here. Essentially, this centrifuge, what it does is it has these vials of blood, and it rotates them at a very, very fast speed. And the centripetal force, it's either centripetal force or it's centrifugal force. No, it's centrifugal force because it's a centrifuge. The centrifugal force will essentially cause the blood cells and the plasma and all the components of the blood to sort of separate because of the force of it. That's a story for a whole another time. But essentially, it might be useful for us to be able to calculate the length of an arc around a circle. For example, didn't mean to do that. For example, how far is it from this point to this point? When I have a circle of radius r, the angle is theta, and we'll call that arc length s. Now, it turns out that actually the formula, like to get the formula for calculating arc length, isn't too hard to kind of think of. If you really think about it, it's just arc length is just a fraction of the circle, right? So if I know how big the circle circumference is, and I know what fraction of the circle I have here based on my angle, then I can calculate arc length, right? For example, if my arc length was half of the circle, right, 180 degrees or aka pi radian, then the arc length should be equal to the circumference times 1/2, right? So that's just kind of showing y'all why this formula works, right? So what I wanted to do was I want to look at this formula and compare what happens when I'm measuring my angles in degree versus radian. So arc length we defined as s. So I have s equals the circumference. Now, no matter what units you're using to measure a angle, the circumference is always going to be 2 pi times the radius. Now, to calculate the fraction of the circle that I have here, all I got to think about is, well, how much of the circle do I have? I have theta degrees. And how much of the circle is there in total? Well, one full revolution in degree, we said before, was 360. So in the end, to calculate an arc length in degrees, it's 2 pi times the radius times my angle over 360. Now let's look at the same formula, but this time in radian. Essentially, arc length is still s here, right? Circumference is once again still 2 pi times the radius. And to calculate the fraction of the circle that I have, it's going to be my angle in radians, divided by how many radians a full revolution is, which we said before, one full revolution was 2 pi radian, right? Now, something that's interesting, and this is not a coincidence, right? This is actually more of a feature. The 2 pi from my circumference formula will cancel out with the 2 pi from the how much of a circle do I have, right? And I'm left with my arc length is equal to r times theta in radian. This is actually this is due to literally the way that we've defined circumference, I mean radian measurement in terms of the circumference. On the other hand, if you look back at our degrees, what we have is 2 pi over 360 as kind of like a coefficient, right? This is just a constant. And then we have the radius times theta. So you can see right away that actually the formula for calculating arc length in radian is much simpler than in degrees. And what happens is that actually beyond arc length, in just tons and tons of application of angles and trigonometry, this 2 pi over 360 fraction just keeps repeating itself, keeps reappearing whenever we're working in degrees, right? Especially in a really terrible way in calculus when you work with trigonometry and such in calculus, you end up getting this fraction just reappearing over and over and over. It's kind of a little bastard. But what's happening is actually this is nature. This is literally like the natural like order of like the mathematical order of the universe. This is nature literally correcting us. They're saying, yo, your units that you're using to measure this angle, we got to convert this shit from degrees into the good stuff, right? Radian. It's literally doing it for us. So this is that's a long-winded way to say that essentially radians makes tons of these applications in the future with angles measurements a lot simpler. So at this point in time, you might be wondering, what actually is a radian, right? You may not have been, but I'd hope you might have thought about that. So to think about it, let's take a look at a circle again. Let's draw ourselves a circle. Oh, that circle's kind of ugly. We'll just fix it up a little bit. And now it's beautiful. And we have a radius on this circle. Now, what I would like to do, we'll call this radius r, right? What I'd like to do is let's say that this angle here, this other angle radius, which is also r, of course, is the angle where I have 1 radian, 1 rad, right? Now, something that might be interesting to look at is now that we just calculated arc length, let's look at what is this arc length going to be here. Well, as we saw before, right, arc length is equal to the angle times the radius, right? But our angle here we said was 1 rad, so actually this arc length is equal to the radius. What you can see is that actually radian is a measurement of angles. Radian is a measurement of angle such that 1 radian of angle is 1 radius around the circle. So 1 radian is equal to 1 radius. That's where the name comes from, by the way, around the circle. Now, if 1 radian is 1 radius around the circle, how many radians is the full circle, right? Well, the full circle we said was 2 pi radiuses, right? This is why a full rotation, this is why 1 full rotation is equal to 2 pi radian. So essentially, y'all, radian measurement is just a connection between the radius and the circumference of a circle, as we defined from the very beginning. So the last thing I want to do with, in terms of the context of discussing radians and radian measurement and kind of introducing it, is let's go ahead and place it now. Let's place radian measurement along our unit circle. So remember, y'all, that the unit circle starts with the right positive x-axis being 0 degrees. Similarly, it will also be 0 radian. Oop, I need to draw that in black. 0 radian, right? And we also know that the full circle was 2 pi radian, right? So this position here on the unit circle, the kind of starting and ending position, is both 0 and 2 pi radian. Half of it would therefore be pi. 1/4 would be pi over 2, as we've seen, and so on. Earlier, we also broke down what some of these other 3 measurements would be, right? Half of pi over 2 here is pi over 4. 1/3 of pi over 2. Notice how, by the way, if you ignore this line here, do you see how this is counting 1/3, 2/3, 3/3 of the pi over 2? So I can actually very easily know that 1/3 of pi over 2 is pi over 6. Now, a way I could have viewed that was actually I have 1, 2, 3, 4, 5, 6 of these same sized pi over 6 angles in order to make up pi. And then similarly, as we saw before, right, doubling pi over 6 would be pi over 3. Now, what's interesting, y'all, is that actually I can also find the other angles around here by just kind of counting fractions, to be honest. Watch this. I'm going to count by pi over 2's, right? 1/4 of the circle was pi over 2. 2/4 was pi. 3/4 would be 3 pi over 2. And this was pi, 2 pi. Let's count by the pi over 4's. I have 1/4. 2/4 is 1/2. 3/4, so 3 pi over 4 is this angle. 4/4 is pi. 5/4, so 5 pi over 4. 6/4 is equal to 3/2. And then finally 7/4, so 7 pi over 4. What I'm doing is I'm just counting by fractions, y'all. And then finally we could do the pi over 6's. I've got 1/6, 2/6 is 1/3, 3/6 is 1/2, 4/6, 4 over 6 is equal to 2 over 3. 5/6, so 5 pi over 6. 6 out of 6 is a full. 7 out of 6, so 7 pi over 6. 8 over 6. 8 over 6 can simplify to 4 pi over 3, though, right? 9 out of 6 is 3/2. 10 out of 6, 10 over 6 can simplify to 5 over 3. Oop, I keep tapping that. Finally, 11 pi over 6. Now, these are all the angles, measurements around the unit circle in terms of radian. Now, there's tons of patterns that you can observe here, y'all, and I think that, to be honest, the best way to do it is by looking yourself, but I'll point out a couple for y'all. Notice that all of the angles which are closest to the x-axis, right, all the short angles are the pi over 6's, right? And you'll notice as well that none of the pi over 6's should be a value which is divisible by 6 or has common factors, right? For example, you won't find a 2 pi over 6 because that would simplify 2 pi over 3 here. You won't find a 4 pi over 6 because that simplifies to 2 pi over 3, and so on. The middle diagonals, right? Those diagonals in the middle are always my pi over 4's. So here's pi over 4, and really I'm just counting by them, right? Pi over 4. I have 3 pi over 4 here. I have 5 pi over 4 here. I have 7 pi over 4 here. Once again, notice that none of the numerators are divisible with 4. They don't have any common factors. This is just kind of the common thing about this, because if it did have common factors, it would have simplified. And finally, we got the pi over 3's, right? Pi over 3 is always the tall one. And that's because 1/3 is a bigger fraction than 1/4 or 1/6, right? You can, once again, just like with the unit circle before, the easiest way to do these things is to kind of just learn the first quadrant, and then you just use reflection, right? So what we notice is that essentially 1/6 is less than 1/4, is less than 1/3, is less than 1/2, right? So in the kind of finished unit circle, which you will oftentimes see, it will actually include radian measurement as well as degree measurement, and so on. I'm not going to bother adding that all right now because y'all don't need to see this. And then it will also have all those coordinates, √3 over 2, comma 1/2, and so on. Now, this kind of this is a lot that we've done to talk about the unit circle, talking about angles, talking about coordinates around it. And you kind of might be like, at this point, a little bit confused as to why does it even matter? Why do we care about this unit circle, right? I've tried to do a good job to show you guys sort of the connection between the unit circle and trigonometry. And I showed y'all before in our class on Tuesday about how, or our class last time, whenever it was, I showed y'all about how the connection between the sine function and the heights of the unit circle. What we saw was that, actually, let me go ahead and erase some of this. I'm going to get these guys out of the way too. Let's focus on the pi over 6 function, since I already have the coordinates written there. What we notice is that if I have a right triangle drawn at any of these coordinates, by the way, then what I see is that my angle here is pi over 6, which is also the same thing as 30 degrees. The side lengths are 1/2 here, root 3 over 2, and 1. And because of the way the unit circle works, because the hypotenuse is 1, it makes finding sine and cosine extremely easy. Because what we can see is this, guys. Essentially, if y'all remember from trigonometry in geometry, we've got this thing called SOHCAHTOA. It's a way for us to remember what sine, cosine, and tangent are. Essentially, y'all, sine is a function which takes the angle of a right triangle, right? So, for example, pi over 6, and it gives you a ratio. Sine is always equal to the opposite, O for opposite, over the hypotenuse. So the opposite side is 1/2, and the hypotenuse is 1. What's 1/2 divided by 1? It's equal to 1/2. In fact, let's look at cosine now, just to get ourselves a little more, see another example. What about the cosine of pi over 6? Well, cosine, we see, is the adjacent divided by the hypotenuse. Adjacent divided by hypotenuse. The adjacent side implies the leg which is next to the angle, which is root 3 over 2 here. So I have square root 3 over 2 divided by our hypotenuse, which is once again 1. So it is equal to just the root 3 over 2. What I want you guys to notice is that the cosine is always just equal to the x-coordinate here. The x-coordinate here. And sine is always equal to this y-coordinate. And I want to show you guys kind of how this looks in general. So here I have just a general triangle on the unit circle. It has angle theta. I use theta because that's a variable. And we see that because it's the unit circle, the hypotenuse is still going to be 1. The opposite side is the y-coordinate, and the adjacent side is the x-coordinate, right? So looking at this, let's look at kind of what would be my sine, cosine, and tangent of this function. Okay, so what we see is, remembering our SOHCAHTOA, what this tells us is that essentially, guys, sine of an angle, and that angle, remember, could be in degree, but it could also be in radian. It actually, because sine is a ratio, right? What sine is it's measuring the ratio of two side lengths in a right triangle. This sine function is equal to the opposite side of the triangle, right? The leg which is opposite of the angle, divided by the hypotenuse of the triangle. Now what we see, y'all, is that ends up actually, the opposite side is always going to be your y-coordinate. In fact, check it out. Even if I have a triangle which is in a different quadrant, if I have a triangle which is over here in quadrant 2, right? Regardless, if my y-coordinate is the opposite side of this triangle, the x-coordinate is the adjacent side, and 1 is still the hypotenuse. And in fact, actually, in this one, with the unit circle, what's cool is that actually, because of the way the unit circle is, I can use any. In fact, you know what? Let's work with that triangle. Why not? I can use any angle. I'm not just limited to angles that are 90 degrees and less. Check it out. This angle is clearly greater than 90 degrees, greater than pi over 2 radian, right? Yet, what's going to happen is that it's still going to produce this right triangle here, right? And so the opposite side of the angle, right, the one away from it, is the y-coordinate. The hypotenuse is 1, so it's always going to equal y. Oops. Let me draw that in white. Y. Let's look at the cosine. Cosine of any angle is always equal to the adjacent. Adjacent means the leg which is closer. Okay, so this x, notice that the leg for x is closer to the angle than y is, right? It's literally touching it, right? Because this is x, this white line here, or this grayish line here. That's x. Notice it's touching the angle. So the cosine is the adjacent divided by the hypotenuse. Hypotenuse is equal to 1, adjacent is equal to x, so in the end, cosine is just the x-coordinate. So something that's crazy, guys, is that we see that the, if this is theta, we see that the coordinates of any angle, right, of any angle along the perimeter of our unit circle is equal to cosine of that angle, comma sine of that angle. Now, this is why the unit circle is kind of useful, right? Because then the unit circle essentially functions as a table for us to remember sine and cosine of different values. And then for completionist sake, let's look at tangent. TOA stands for tangent of an angle is equal to OA, the opposite, which I'm going to abbreviate as OPP, divided by the adjacent, ADJ. What is the opposite side? It's the y-coordinate. What's the adjacent side? It's the x. So actually, guys, tangent is equal to y divided by x. In a sort of, this is not really saying that, this is saying that we'll focus on later, but in an interesting way, that actually definitionally means that tangent is equal to sine, right? Because sine is y, divided by cosine. And this is actually an interesting kind of feature of trigonometric functions. So in our class, what we're going to do for this week and what we're going to do in on Friday or on our problem set day is we're going to be looking at the sort of the what is the sine, what is the cosine, what is the tangent of various angles. For example, I could ask you guys, what's the sine of 120 degrees? What's the cosine of pi over 4? What's the tangent of 0? Right? And we could actually very easily calculate these things using our unit circle. And what I want to show you guys is that I don't actually myself have the unit circle memorized. In fact, what I do is every time I'm trying to evaluate one of these things, I'm kind of thinking about the unit circle because I'm lying. It's not that I don't have the unit circle memorized to sort of a degree. What I have memorized is kind of how did we originally derive it? I think about where is 120 degrees as an angle? Well, I know 120 is greater than 90. In fact, it's 30 degrees more than 90. So I know that it's the angle. It's an angle which is over here, right? 30 degrees more than 90. So what is the triangle that results? Well, if it's 120, then actually this is a 60-degree angle, right? Because if you think about it, 120 plus 60 makes the full half circle. That's kind of contradictory, full half circle. All right. And so it's like, okay, so then what is the coordinate here? Well, I notice that this is the tall one, right? And the tall one, right, always has this combination, 1/2 root 3 over 2. Because root 3 over 2 is bigger than 1/2, right? I hope you guys see that. This is actually, root 3 over 2 is greater than 1/2. That's kind of relevant to our conversation that we had, to a conversation that I had with some students previously this week. And the only thing I need to change here is that I notice my triangle here is in the negatives, right? So the x-coordinate should be -1/2. So what I've done here, guys, is I've actually shown y'all that kind of my thought process as I'm trying to evaluate sine of 120. So I know that sine is the y-coordinate. What's my y-coordinate? It's root 3 over 2. Okay, fine. Cosine of pi over 4. Where is pi over 4? Well, pi over 4, I know, is 1/4 of pi, right? Pi is half the circle. So oh, pi over 2 was 90 degrees, and half of that is here at pi over 4. Oh, look, that's the diagonal, right? And what I remember, guys, I don't remember perfectly what the coordinates of pi over 4 is. What I more am doing is I'm saying, oh, this is the diagonal one where the side lengths are equal to each other. That's the one that had root 2 over 2. So what do I actually have memorized, guys? If you're like curious, those of y'all who are kind of trying to figure it out, all I have memorized, guys, is the possible coordinates. I know that 1, 0, or like 1 and 0 are some of them. I also know that root 2 over 2 is one of the combinations. And I also know that root 3 over 2 and 1/2 are the other ones. These are the only 5 numbers in the unit circle that really exist for coordinates. And everything's just kind of washing a mixture of them. So cosine, we know, is the x-coordinate. My x-coordinate here is root 2 over 2. So cosine of pi over 4 is root 2 over 2. What do you know about that? Tangent 0. Well, at 0 degrees or 0 radian, it didn't even tell me. At 0, although there's no degree symbol, so actually it's implied that it's radian, guys. If there's no degree symbol, it is radian. Tangent of 0. Tangent is the y over the x. What's my y-coordinate? 0. My x-coordinate's 1. 0 over 1 is 0. So you guys can see, actually, evaluating trig functions is actually, I hope, not too crazy. Now, I would totally expect y'all to have out a unit circle as you're practicing these. This whole trick that I'm doing here, where I'm trying to figure out the triangle, and it's kind of, this is like what I do as someone who's used the unit circle a bit. I totally understand that as people who are just getting used to this, there's a lot to remember, there's a lot going on. I would expect you guys to always have your unit circle in your notes, have it available as you're evaluating these things. With that in mind, y'all, this is the end of the video. So just a recap of what have we done, right? What is it that we did? It's actually a lot that we did, guys. This is a lot of trigonometry. We derived the unit circle, right? We took the first quadrant and we expanded it to the rest. We did a lot of understanding of radian measurement, right? We talked about what is radian measurement. It is the idea where we're connecting the radius to the circumference of a circle in our measurements for angles. 2 pi radians is 1 full rotation around the circle. And then finally, we connected that all back to the unit circle and took a look at some basic trigonometry. That's SOHCAHTOA, right? Remember, guys, this SOHCAHTOA is a lifesaver. It's kind of weird, it's kind of random, but it sounds kind of funny. It's an interesting word to say, and it helps us remember those trig ratios. So I will see y'all during our next class session, where we will be working on a problem set to practice these ideas. Have a nice day.